Atom is another type of an optimizer. The way I think of atom is basically it's RMS prop plus momentum. Okay? Atom stands for adaptive moment estimation. A moment is the statistical term. So there's a first moment, a second moment, and so on. A first moment is the mean, a second moment is a variance, and there are other moments as well. It's really very much like RMS prop plus momentum with a small change. So we are going to go ahead and have E. We're going to have V, two hyperparameters. We're going to make a slight modification to E and V for this reason, right? We initialize E equals V equals 0 to begin with. The problem is, as we are early in our estimations, we are off in our true estimation. So let me give you an example. Let's say you have seen one gradient. What's your best estimate of the mean of that gradient? Well, that gradient, right? But that's not what we have here. What we have here, let's say beta is 0.9. Then we have 0.9 times 0 plus 0.1 times our current gradient. So our estimation, our exponential moving average, which is estimating our gradient, is actually down by a factor of 0.1. Right? It's 0.1 of what it should be because of the fact that we initialized E equals V equals 0, and so we've got this weighting of 0. It's coming on over time, right? We're going to, as we have alpha to the k or beta to the k large enough that these old estimations of 0 aren't going to really matter. But what we can do is actually correct this because, again, of the fact that we're initializing it to 0. So if we look at the first estimation at time 1, we have our current squared gradient, but we multiply by a factor of 1 minus gamma. So what we'll do here is just divide by 1 minus gamma to the t. So the first time through, we're going to have multiplied by 1 minus gamma. We'll also divide by 1 minus gamma. The second time through, we had the 0 matters a little bit less. Right now we have two estimations of the squared gradient. The current time step, the previous time step. 3 time steps ago is still 0. We're going to go ahead and have a slightly less of a correction. And over time, as t gets larger, this alpha to the t gets smaller and smaller, and e to the t hat just approaches e. Similarly, we're going to have a v t hat equals vt over 1 minus beta to the t. So these basically just correct the startup of this root mean squared estimation of the sum of squares and the estimation of the velocity. And then what we do is go ahead and say, okay, we have theta equals theta minus, well, our learning rate is, let's just go ahead and write our learning rate separately. So our learning rate equals r lambda over epsilon plus the square root of e, and then theta equals theta minus lambda times. But now, instead of an RMS prop, where we would use the gradient itself, now we're going to use the v hat. And here, we'll use e hat. So if we want to put in some time steps, just to kind of see, the theta at time step t equals theta at time step t minus 1 minus lambda at time step t and v hat at time step t. It's exactly combining RMS prop, because all of this looks like RMS prop, plus a little fix to the initial values of e and t, the first few values. And then instead of multiplying with a gradient, we multiply by our velocity.